Welcome to the class of material selection for mechanical design. We are at module 3 and now we are focusing on, after this knowledge of crystal structures that we have discussed so far and the effect of crystal structure on the mechanical properties, mostly on metals, we want to see now that how certain materials, particularly metals, and among them also the iron and iron alloys are suitable for product design. So, we have to look into it from the point of view of the specific properties of different types of iron and iron alloy. That will be the focus of this lecture. So, I will start with the classification of ferrous alloys, the types of steel, effect of impurities and cast iron, because iron has a very wide range of possibilities. And remember that it is the most versatile structural material for many mechanical systems for thousands of years. Okay. So, every possible variants that has been designed have very important role in terms of developing any mechanical system. So, I will talk about classification of ferrous alloys, types of steel, effect of impurities and cast iron. Now, metallic alloys, which would clearly indicate that you have a base metal, something like iron or something like aluminum or something like nickel or copper. With that, you are substituting some of the atoms by some other alloying elements. That can be metal, can be non-metals, but that is the way we form the metallic alloys, and they can be grouped into two categories: the ferrous category, where the base metal will be iron, and the non-ferrous category, where the base metal could be aluminum, copper, zinc, nickel, titanium and other. Now, today we are going to focus on ferrous elements, and there are two broad groups, that is the steel group, where the percentage of carbon is less than 2%, and the cast iron group, where the percentage of carbon is greater than 2%. On that basis, though we will broadly divide, but we will soon see that there are many ramifications of these groups even inside steel or inside cast iron. Now, as I told you that the Iron Age began 3000 years ago and it is still continuing. Well, one of the reasons why it is still continuing is that it is quite abundant in earth. Okay? So, it is not rare, and also it is easily processable and recyclable. It is also one of the cheapest material, that is why. Now, carbon mixing with iron became, although initially serendipitous, but later on became almost regular in nature, and that is because people understood that it forms an interstitial solid solution. Okay? That means, imagine that this is a iron atom, this is an iron atom, and this one and this one. So, the space that is inside them, okay, is good enough for smaller atomic radius materials, and carbon as one material, very abundant as an organic material, let us say from wood or charcoal, you always get carbon. So, you can easily mix parts of carbon in the iron, and that goes inside the iron's interstitial space. As a result, you get some very good properties that we are going to see. So, the atomic radius of the carbon is as 0.071 nanometer, and that is much less than 0.124 nanometer of iron atom size diameter. So, it can very easily go and fit inside. So, thus carbon became a natural companion of iron. Now, iron, however, possesses many different allotropies or forms. Okay? For example, when the temperature is less than 770 degrees centigrade, we get iron as ferrite, alpha iron we call it, which is a ferromagnetic BCC crystal structure. From 770 to 912 you get beta iron, which is paramagnetic BCC crystal structure. Then if you increase it further 912 to 1394 you get gamma iron, which is austenite, and that has FCC crystal structure. And this austenite we will later see play a very important role in defining the mechanical properties of iron. Then beyond 1394 to about 1538, beyond that naturally the iron melts, you get delta iron, which is again a BCC crystal structure. So, BCC, BCC, FCC and then again BCC. So, iron changes its forms with respect to temperature. If we keep that point in our mind, then what we can do is that we can heat up iron, take it to a particular crystal structure and then quickly quench it to retain that structure. So, that that crystal structure, the benefits of it we can sort of extract. So, that is why these phases are important for us. Now, today what is the scenario? Okay, at least some I do not have the most recent one, but world crude steel production till 2015, if you look at it, then it has reached about 1621 million tons, in which China has one of the major shares, but India also has significantly high contribution in terms of steel production. So, you can see that the growth is ever increasing. There are a bit ups and downs, but on the whole the growth is increasing for iron. There is no chance of any receding from that particular pattern. Now, these are the top steel producing countries, and you can already see that India has a very important part in it. Okay? In fact, if some of the Japanese companies which has joined now with KANPUR-NPTEL, if we consider that, then this is the highest. For example, today Nippon has joined. Okay? So, this becomes the highest contributor in terms of 97 approximately million tons, okay, maybe even more. So, also we have other big groups from India like Tata Steel Group, SAIL, Jindal Steel, each one of them have tremendous contribution in steel production, and that is why in the world map India has one of the biggest footprint, always among top 2 or top 3s in terms of steel production. So, the steel remains a very important part of our economy. Now, as I told you that steel is always less than 208% of carbon. So, we can further divide it into two types of steels, low alloy steels, okay. So, which has less than 1008% of any alloying elements, not just carbon, but any alloying element, and greater than 1008% of alloying elements. Okay. So, carbon is less than 2%, fine, but there can be other alloying elements also. In low alloy element, their role is much lower. For example, low carbon steel, in which carbon is only about 0.25%, and then medium carbon steel, in which carbon will be about 0.25 to 0.6, and then high carbon steel will have 0.6 to 1.4, but they will be having other alloying elements, and depending on that the nature will change, and we will soon see it. Now, in the high alloy steels where greater than 10% of carbon is present, we have one of the big category which is called stainless steel. It has greater than 10% of alloying elements present, and that is about greater than 11% is chromium, and then of course, we have the tool steel. So, these are the groups that we are going to see. Now, first we are going to see the low alloy steels, which by definition will have less than 28% of carbon and less than 10% of other alloying elements. So, let us look at those groups first. Now, as per the AISI definition, American Iron and Steel Institute, for plain carbon steel, when no minimum content is specified for the alloying elements, for example, chromium, cobalt, molybdenum, nickel, titanium, tungsten, vanadium and zirconium, etc., then to be added to obtain a desired effect, and when the specified minimum amount for copper does not exceed 0.4%, then also it is a plain carbon steel, or when the maximum content for any of the following element does not exceed the percentage, like manganese not more than 1.65, silicon 0.6, copper 0.6. Okay. Then what we get is something which is called plain carbon steel. Effect of increasing the carbon content in the steel will be in terms of hardness and strength, okay, because the carbon is going inside the interstitial space, that will make the dislocation difficult to move, and then it will also decrease the weldability. So, you are increasing the property in terms of hardness and strength, but it is going to decrease the weldability, it is also going to decrease the ductility, and naturally it will decrease the machinability as the ductility comes down. So, even though with the addition of carbon you get a high hardness and strength, what you are going to suffer is in terms of this weldability, ductility and machinability. So, that is where the optimum amount of carbon comes into picture. Okay. Now, when we talk about low carbon steel, that would contain less than about 0.25% of carbon, and you get a mild steel. It is relatively soft and weak, outstanding ductility, 25% you can elongate, and toughness is also there, high machinability and weldability, least expensive to produce, and tensile strength is about 450 to 550 megapascal. So, low alloy steel will be having other alloys, of course, other than 0.25% weight of carbon. You will be having copper, you can be having vanadium, nickel and molybdenum, all up to 10 weight percent. Okay. High strength and corrosion resistance than plain low carbon steel you will see in low alloy steel, because you have all these alloying elements, and the tensile strength can go farther from 550 MPa to 700 MPa when you introduce these alloys inside the low carbon steel. And this is something which has huge use for all structural applications like steel structures, for beams, for channels, nuts, bolts, wires, tin cans, etc. So, that is what is the low carbon steel group. There is a very special group of a low carbon steel, and this is called drawing quality low carbon steel, which has a big use in automobiles. Now, I would like to tell you a bit of history, that automobile initially were all wooden. The famous Mr. Bainge, who started industrially developing automobiles, the most of the system except the wheel was actually wooden in nature. It is only when Ford thought of mass manufacturing it, the Model T came into account. Then in USA, in America, this all started to be made of metals. Now, why metal is needed? Because with the metal, now you can actually give more complicated shapes to the system. For example, this is the fender part, you can give a nice shape. Then on the bonnet, you can give a nice curvature. On the windows, you can give a nice curvature. So, you can actually aesthetically make the system much better. However, if you want to do that, the steel will be subjected to a lot of deformation, large deformations. That means, in other words, it should have a deep drawing capability. So, for all the aesthetically pleasing systems, the deep drawing capability is required on the steel, and that is how the drawing quality steel or DQ steels were developed. Now, there are two important qualities of a DQ steel. One is a high N value, that is the strain hardening exponent, and that is about 0.22 to 0.26, that actually delay the local necking. As you know, the steel always fails as a ductile material through the necking process. But if you have about 0.22 to 0.26, you get a large plastic deformation, fairly large, and you can get also work hardening and strain hardening before the necking occurs. So, you get a high N value for this drawing quality low carbon steel. And along with that, you also get a high R value. R value for this is about 1.4 to 1.8, that actually suppresses the thickness reduction as you are drawing the steel, because if the thickness if it gets thinner more and more faster, and then what happens, it may fail. So, that is what the high R value means, it resists the reduction in terms of the thickness. Now, if you look at the DQ low carbon steel, you see that the carbon content is really very low. Okay? Although, in order to be a low carbon steel, you should be less than 0.25% of carbon. Here it is only 0.03 to 0.08. So, the carbon content is really very low. Significant content is from manganese and a small content of silicon, phosphorus, sulfur. Okay? So, these are the most important contributors in the drawing quality for the low carbon steel. Now, I want to talk a little bit about the N value and the R value. Okay? So, N value is also known as the strain hardening exponent. The strain hardening exponent, which we denote by N, measures the ability of a material to increase its strength as it plastically deforms, because you know that there is this region where the strength actually increases because of the strain hardening, and it is defined through an equation called Holloman equation, where sigma is k epsilon to the power n. Okay. So, if sigma is k epsilon to the power n, I can actually take log in both the sides. So, log k will be what? Log sigma will be log k plus n log epsilon. Okay. So, in the log plot, this will be more like a straight line equation, y equals to c plus mx. Okay. So, in that equation, the n works like the slope, and the slope between what? The slope between log of epsilon and log of sigma. That is why n is d log sigma divided by d log epsilon, where now you have to know this, that this sigma is the true stress and epsilon is the true plastic strain, and k is the strength coefficient. Okay. So, if we know the stress strain diagram, and if we can get the true stress and true strain plot in a logarithmic scale, we should be able to find out that what will be the value of n. And if the slope is more, then you are going to get a better drawing quality of the system. Now, let us look at some of the typical N values for automobile application. Okay. For mild steel, it is about 0.18. For DQ steel, it is 0.2 to 0.24, so quite higher. For IF steel, it is actually called interstitial free steel. It is about 0.25 to 0.30, which is even better. And you compare it always steel with its competitor like aluminum, it is 0.18 to 0.22, which has slightly less drawing quality. The dual phase steel, I will talk about it soon, is having also a reasonably good value in terms of the drawing quality. Okay. How about the R value? R value is nothing but the plastic strain ratio. So, the R value essentially indicates the resistance I told you of a sheet metal to thickness reduction. It is defined as R equals to epsilon width over epsilon t, where epsilon width is the plastic strain in width direction, epsilon t is the plastic strain in thickness direction. Now, if an R value is high, okay, so what does that mean? It means that the thickness direction epsilon t is smaller. So, if this goes down, then this goes naturally up, right. So, that means strain in the thickness direction is going to be smaller if the high R value if you can get, and that has a good possibility that you can deep draw the material. Okay, that is ideal for deep drawing. So, let us look at the R values for automobile application. With mild steel as the baseline, it is about 1.0. DQ steel, the drawing quality steel, will have an R value up to 1.8. Interstitial free will have up to 2.5. Aluminum's R value is very small. See, that is one of the point where later on I will discuss that even though aluminum can be used to make a very lightweight automobile, but because its drawing quality is very small, that would mean that it will have a thinning of the thickness, and that would mean that aluminum is susceptible to failure during the drawing process, which means if you want to give some complicated shape of automobile using aluminum, then you have to take lot of additional precautions. Stainless steel you can see is also not having very high value. So, the best things that you are achieving is from the DQ steel and interstitial free steels. Now, let us come to medium carbon steel. Medium carbon steel would contain about 0.25 to 0.6 weight% of carbon. So, that means as the carbon increases it is going to be stronger. So, they are stronger than low carbon steels, but of course, there will be low in ductility and toughness. Now, then we will not use it as simple as that for automobile body, but we can use it for other applications because it has a good wear resistance. Okay. So, that is why they are used as the rail wheels, as gears, as crankshafts. Okay. So, plain carbon steel's tensile strength up to 850, and if you alloy this steel it can go this strength up to 1900. So, that means it is quite good in terms of the strength point of view. Now, if I go to high carbon steel even higher than this, that is 0.6 to 1.4, then you get the hardest, strongest and least ductile carbon steel, and this can be alloyed with say chromium, nickel, tungsten, molybdenum and vanadium, and then this will have applications in terms of cutting tools, embossing dies, saws, concrete drills, etc. Okay. So, that is about the high carbon steel. Now, if we go for high alloy steels which has greater than 10 weight% alloys, then as I have just now told you that tool steel is one of the very important one which is continuously used in drill bits and other rotating cutting tools. It can withstand higher temperature without losing its hardness and toughness. So, one example of tool steel is this HSS 1841, which has about 18% tungsten, 4% chromium and 1% vanadium, with a carbon content remaining about 0.6 to 0.7%. The cobalt high speed steel, one of these varieties of the same high alloy steel, that is used for increased heat resistance, and the last one variety in this category is molybdenum high speed steel, which in which molybdenum increases the hardness and wear resistance, because they are mostly used for cutting tools. So, these are cost effective replacement also for tungsten. Tungsten is more expensive. So, you can see that almost for all the different types of cutting tools you use basically the tool steel, which is actually a high alloy steel. And in the high alloy steel category we have the stainless steel also, which is highly resistant to corrosion and can be used for a variety of environment where corrosion is a factor. Let us say for cooking, let us say for subsea structures. So, you can use it. The condition is you have to use chromium at least 11 weight%. So, there are steels like 18H stainless steel which has 18% chromium and 8% nickel, and this will have applications for cryogenic vessels, for food processing, gas turbine parts, high temperature steam boilers, heat treating furnaces and nuclear power generating units. Now, one thing that is generally done on the chromium is that a very thin layer of chromium oxide is formed on the chromium. Okay? That is the Cr2O3. This is called passivation. Okay? And through that you can increase its corrosion resistance. Now, let us look into the effect of alloying elements on steel. If you alloy boron, it improves hardenability, it becomes harder, but the machinability is not lost very much. If you use chromium, it improves the oxidation at high temperature and corrosion resistance. Okay. Nickel and molybdenum can also do the same. Cobalt and tungsten improves generally the strength and hardness at elevated temperature. Sulfur improves on the other hand the machinability when combined with manganese, and if you only use sulfur without manganese, it may actually increase brittleness and lower impact strength and ductility. Manganese has a good effect on hardenability and wear resistance, and it also counteracts the brittleness caused by sulfur. Molybdenum improves hardenability and toughness. So, it improves the elevated temperature strength, and elevated temperature strength is something is very much important for refractory type of applications and creep resistance. Then we have nickel, which increases strength and hardness without sacrificing ductility and toughness. We have vanadium, which increases strength, hardness, wear resistance, resistance to shock impact and high temperature, and then titanium, which improves strength and deoxidizes the steels. So, this is a long list of different alloying elements, how it actually works on the steel. So, the same thing I have tried to depict here through the bit of graphics in terms of some important mechanical properties, like you want to have hardenability, go for chromium, go for manganese, molybdenum, vanadium, etc. High temperature, again molybdenum, nickel, they would do very well. Ductility and toughness, nickel plays a very good role. Wear resistance, you have the tungsten. Promote fine grain size, vanadium plays a very important role in promoting the fine grain size. Corrosion resistance mostly comes from chromium, and that is why the stainless steel is of chromium. So, this actually graphically tells us that what are the things that are the contributor to the desirable properties while making the steel. Now, I will talk about some very recent steel elements that are used highly in the cases of automobile design. So, one of them is DP 400 and DP 700 steel. DP has these two, 400 MPa strength and 700 MPa strength of steel. Now, DP indicates actually dual phase. Okay. So, these are specifically good for lightweight crash-worthy automobiles. In the dual phase, what are the phases it has? Soft ferrite matrix, typically 70 to 90%, and hard martensite island in it, that is typically 10 to 30%. Now, as I told you that DQ steel was once very good for till 1970s, but then they were not very light. Okay. So, in order to make it lighter, high strength low alloy steels started to be developed, okay, and for which you can make it sort of a structure such that it can increase the crash safety even if you sort of reduce the section thickness. Now, the way you get the dual phase, because you need to get both the phases, is that you do a hot rolling and then a cold rolling. So, heat treat in the intercritical region between 730 to 850 centigrade and then rapidly cool it. The resulting microstructure will have ferrite formed during this intercritical annealing as well as martensite formed from the remaining austenite during rapid cooling. So, it becomes a material which has two phases in it, okay, and then each of the phase contributes separately in terms of manufacturability, in terms of strength, etc. The another important steel that has come up from the DPE is the trip steel. Trip steel is called transformation induced plasticity steel. That also has two groups, 450 MPa and 800 MPa, lower strength and higher strength. Now, trip is different from the dual phase because it contains a mechanism of retained austenite transformation into martensite during plastic deformation. As a result, it actually improves its strength during the process of work hardening. That is the good part of this type of steel. So, it has now not just the ferrite and the martensite part, but it has ferrite which provides ductility, it has bainite which provides strength and supports austenite stabilization. It has a retained austenite, that is the beauty, which transforms during deformation and make the system harder, and martensite small amount which gives additional strength. So, that is what is the trip type of a steel. The trips composition gives it. So, this is in the AHSS property and it gives a very high strength with excellent ductility. Okay. And rest of the functions that I have already talked about for the trip. Now, this is the typical composition of the tip. Okay. That is, it has about 0.18% of carbon, then it has about 1.5% of manganese, 0.05% of silicon, 2% of aluminum, 0.01% of phosphorus, 0.02 of chromium, 0.002 of nickel and 0.003 of nitrogen and 0.003 of titanium. Okay. So, this each one of them, and that is through the long research that the companies create such systems, have an enormous role in that work hardening process, and this is used by big companies like General Motors. Okay. Now, if you look at it, that is just a comparison of trip with respect to the dual phase or the mild steels. You look at the tensile strength that you can get 503, the yield strength is 831, that is enormous, and also if you look at the total elongation, the N factor is 0.236, that is quite good. No, it is not very high, but it is still quite good. Okay. So, this I have taken this data from a book by Professor P.K. Malik on lightweight vehicle design. Now, from there I come to another very interesting development in the steel, that is called twining induced plasticity steel, TWIP. You remember during the crystal structure I have talked about twining and dislocation. Okay. Twining plays a very important role in terms of giving you a large elongation, but the system will not fail because the twining stops the dislocations movement. So, this is member of a second generation advanced high strength steel or HSS. Now, this has an FCC austenite structure with a high level of manganese that actually gives this extraordinary kind of a deformation capability. The tensile strength for such a system goes up to 1000 megapascal and the total elongation is greater than 50%, that is unbelievable, and twining successfully restricts, as I told you, the movement of the dislocations. Now, here I am comparing between the DQ, the dual phase steel, the trip steel and TWIP steel. Okay. So, what you can immediately see that in terms of density there is hardly any change. Okay. So, specific capacities, if you look at it, then of course, like yield strength, the maximum yield strength you are going to see in one of the dual phases DP 800 and also quite good in TWIP and TRIP. Ultimate tensile strength is about 900 in DP, 850 in the trip, but 1200 in TWIP. that is something that is good, because it actually keeps on hardening during the work hardening process. So, that is the beauty of TWIP steel. So, that at the end it is not the yield strength, but the ultimate tensile strength when it is going to fail, that is going to be so high for this material TWIP. Elongation wise, you see, it is giving a very high scope of 45 to 70%. So, you can literally make many things out of it, and total elongation is 50 to 80%. Now, if I look at some more properties like the strain hardening, again this TWIP is the best. Plastic strain ratio, that also it is good, and trip is also good. So, that means they are not going to fail during the drawing process. Young's modulus wise, there is hardly any change, that is the good part of it. Work hardening rate is extremely high for TWIP, so true is for energy absorption, crash worthiness and formability. However, in terms of a spring back, DP 800 is good. Spring back is important to give the dent resistance, or even if there is a dent, it should be like a Coke can, it will snap back. So, that DP 800 has that property. Weldability wise, DP 600 is excellent, DQ low carbon steel is excellent, but these other groups, they do not have good weldability, particularly for spot welding. And relative cost wise, you see these are very high, okay, whereas the cheapest one is the DQ low carbon steel. Okay, there are two other varieties of stainless steel, I should say. One is 304, another is nitronic 30. Now, 304 is a very common stainless steel, it is called AISI 304, and it is used as austenitic stainless steel worldwide. It is also known as 18-8 stainless steel because it has 18% chromium and 8% nickel. The nitronic steel has this thing because it is nitrogen strengthened austenitic stainless steel. It's developed primarily for applications that require higher strength than 304 while maintaining this excellent corrosion resistance. So, that is the nitronic 30. You get of the similar corrosion resistance, but you get a higher strength in comparison to the 304 stainless steel. Now, I will come to the last group, that is the cast iron types, okay, which has greater than 2% of carbon. Now, there are some varieties of it. One of them is called grey cast iron. It has carbon content from 2.5 to 4%, and graphite exists in the form of flakes. You can see the flakes of graphites here. This graphite flakes gives actually self lubrication property and vibration damping capacity. So, cast irons are one of the best in terms of vibration damping, okay, and strength and ductility are also much higher under compressive loads. So, that you can basically use such a system in terms of below the railway lines, because you get a good absorption of vibration, reasonable tensile strength, not very high, modest. So, this is no wonder it is used for base structure for machines also and heavy equipment that are exposed to vibration. We also have white chilled cast iron and malleable cast iron. In the white chilled one, much unlike the grey one, there is no graphite. So, carbon in the form of carbide you are going to get. So, this is formed by rapidly cooling molten iron with a large percentage of carbon. So, very hard, wear and corrosion resistant, almost non-machinable, and this is used as rollers in the rolling mills. We also have a malleable variety of cast iron, and that is formed by heating the white cast iron between 800 to 900 degrees centigrade for a prolonged time, and that leads to the decomposition of the cementite forming graphite in the form of cluster. So, graphites are here not evenly distributed, but forming clusters. As a result of these clusters, this is highly shock resistant and tough, and it has a tensile strength which is also quite good and can be hammered to small thicknesses. So, that is why this type of a cast iron is used in connecting rods, transmission gears and differential for automotive industry. Now, we also have some uses of ductile, nodular or spherical cast iron. This is obtained by adding some small amount of magnesium on the gray cast iron, so that you can get a higher fluidity, you can get a higher tensile strength, toughness, machinability, weldability, etc. So, that is the ductile or the nodular cast iron. Then there is one interesting form which is called mottled or compacted cast iron. This is product in between gray and ductile cast iron, and carbon is partly free and partly in combined form. The graphite here has a worm like appearance. So, this gives better resistance to thermal shock and lower oxidation at elevated temperature, and that is why it is used for diesel engine block where the temperature continuously changes in the combustion phase, exhaust manifold, gearbox housings, flywheels, etc. So, there if there are impurities in cast iron, for example, if you add silicon, then on top of the carbon that we do, it provides formation of free graphite, makes iron soft and easily machinable. If you use sulfur, it makes the cast iron hard and brittle, and above 0.1% makes gives unsound casting. Manganese makes it hard by formation of carbide, keeps control over harmful effects of sulfur, and phosphorus imparts fusibility and fluidity, but induces brittleness in the system. So, this is where I am going to end today, okay, and with that the module 3 is over, and then we will go to module 4 in the next lecture. Thank you.